Welcome back. So this was the quiz question before the break. And here is the answer. So, as you know, to get the marginal rate of substitution, we have to take MUA over MUB. MUA in this case is the derivative of my utility function with respect to A. So B is the constant here. So if I take the derivative with respect to A, I get B. And my marginal utility with respect to B equals A. So if I calculate my MRS, I get B over A. But my consumption of apples is 4, the consumption of bananas is 5, so that gives me 5 over 4 as my MRS in this case. Which brings us to section 4.3. So in 4.2 we talked about your preferences, your utility function, what you want, what you really want. But now we are going to look at what you can actually afford. And that's actually straightforward, right? So suppose that you have an income on the left-hand side here. Suppose that you consume two products, X and Y. The price of product X is given by PX, and the price of product Y is given by PY. So your total outlays, this will be the amount of money that you spend on product X, it's just the price times the quantity. This will be the amount that you spend on product Y, just price times quantity. So this is the total amount that you spend. And of course, this is a world in which there's only one period. You cannot save money. You have to spend your money or lose it. And then, of course, you will make sure that you spend your entire income. Because if you don't, you have money left and you can use that money to buy more. And since more is better, that would increase your utility. So that's why we look at this income. You can rewrite it a little bit. You can write it so that it becomes easier to show in XY space. And for example, if you buy socks and t-shirts, if your income is 50, price of socks is 5, price of t-shirts is 10, then plugging all those things in here gives this budget line, budget equation. And that looks like this in this case. So you can just afford everything that is on this green line. If you spend all your money, your 50 euros on socks, you can buy 10 pairs of socks. If you spend all on t-shirts, you can buy 5 t-shirts, but you can also buy any combination of the two. So that is that budget line. What about consumption? Well, you can afford everything within this area, right? If you are here, for example, you consume 2 pairs of socks, 3 t-shirts, and that is within your budget line, so you can afford that. However, any bundle that is above your budget line, you can not afford. You simply don't have enough money to buy 8 pairs of socks and 4 t-shirts. So this triangle here gives you all your feasible consumption bundles. What's the slope of this line here? That's minus px over pi, and that's minus 1.5 in this case. And again, the best way to understand these kinds of things is just to write it down for yourself, draw the curve, play around with it, and then you will see. Okay, so what happens if I play around with prices or incomes? What happens to my budget constraint? Okay, first panel. Suppose that the price of socks increases. What happens? Well, if I still spend all my money on t-shirts, nothing will change, right? The price of t-shirts hasn't changed, my income hasn't changed. So if I spend all my money in t-shirts, I can still buy 5 t-shirts. However, if I spend all my money on socks, then I can now buy fewer socks than I did before. So this point is not going to change, but this intercept is going to change. Again, my budget line will be a straight line. So in other words, the line rotates inwards. What if I change? So I lose these feasible bundles, right? I cannot afford them anymore after the price increase. Okay, so what happens if we increase the price for t-shirts? Something very similar. If I spend all my money on socks, then I can still buy 10 pairs of socks. But if I spend all my money on t-shirts, I now can only buy 2.5 t-shirts rather than 5, so the price has doubled. So this gives me my new budget line, and this gives me my new feasible bundles. And this is my loss of bundles. Okay, last change. Again, this is the old budget constraint. What if my income is lower than before? The income is halved from 50 to 25. In that case, if I spend all my money on socks, I can only buy 5 pairs of socks now rather than 10 that I had before. If I spend all my money on t-shirts, I can only buy 2.5 rather than the 5 I bought before. So my whole budget line is going to shift inwards in this case. And these are the feasible bundles that I lose because of that. So that's very important to be able to play around with these budget constraints and see what happens if prices or income change and interpret that change. Okay, so here's another example. Suppose that we have James. He has $40 or euros per week, and he has a consumption of movie tickets and burritos. Movie tickets cost 10, burritos cost 5. Question, what is an equation for the budget constraint? What does it look like? And what happens if the price of burrito changes to 8? Okay, let's see. So, income was 40, price of burritos was 5. B represents the consumption of burritos, price of movies is 10. M represents the consumption of movies. So in other words, this is my budget line. I have movie tickets on the vertical axis, burritos on the horizontal axis, so I should write this as M as a function of B, right? So if I do that, I end up here, so this is going to be my budget line, and that's drawn here. And again, the easiest way to do that is just to think, well, if I spend all my money on movie tickets, my income is 40, tickets cost 10, so I can buy 4 movie tickets. If I spend all my money on burritos, which cost 5, then I can buy 8 burritos, and I can also buy any linear combination of those two. Okay, so what happens after the price of burrito changes to 8? The price of movie tickets has not changed, so this point is not going to change. However, if I spend all my money on burritos, and now I can only buy 5, which implies that this is my new budget line. Okay, so that was a very simple, straightforward budget line. We can also make things more complicated, as we always can. Suppose that there are quantity discounts. Suppose that you have to pay a lower price if you buy a certain number of goods. For example, buy 2, get 1 free. Or there are some limits of how much you can purchase. For example, in the 1970s, there was a maximum on the amount of gasoline you could consume. Okay, how to draw those budget lines, and will also be in the practical this week, if I'm not mistaken. The easiest way to do that is first to draw the budget line without any constraints. So what we have here is a situation in which you buy pizzas and phone minutes. If you spend all your money on pizzas, you get 10. If you spend all your money on phone minutes, you can buy 1,000. But now suppose that you get a discount if you consume more than 600 phone minutes, then the price halves. So that means that my budget line is not going to change for phone minutes below 600, but above 600, my budget line is going to be steeper, right? So this represents the new price. If I spend all my money on phone minutes, then for the first 600, I still pay 10 cents. For the rest, I pay only 5 cents, which apparently implies that you can buy 1,400 phone minutes if you spend all your money on that, but just figure that out for yourself. So what does my budget line look like in this case? Well, that's this kinked thing here, right? Below 600, this is my budget line. Above 600 is going to be like this. So this is my feasible, these are my feasible consumption bundles. Okay, what's next? Section 4.4. So, in 4.2, we had your preferences. In 4.3, we had your income. If you have a certain amount of money, you always want to make the best out of it. At least that's what we assume. We assume that consumers are completely rational, and they do that. So what we're going to do, we want to be on a utility level that is as high as possible, right? We want to get to an indifference curve that's as high as possible, because higher indifference curve means more utility and happier consumers. However, we have to take into account how much income we have and what the market prices are. Okay, so the easiest way to do that is, again, make a graph in my A-B space, or XI in this case. So here two goods, good X and good Y. And suppose that this is my budget constraint. So this gives me all the combinations that I can buy when spending all my money. Okay, so there is a bunch of indifference curves here, and I know that there are many of them, and I know that they are parallel to each other, so this is just one of them. So I could consume here, right? Then I would reach utility level U1. Question, is that a good idea? Well, first of all, important to note, this utility level, it is feasible, right? There are consumption bundles that I can afford that are within my budget constraint, and that are also on this indifference curve. So this is feasible. But I can do better, right? I could consume this, but I could also move a bit over here. If I move over here, then I can still afford that bundle, but my utility level is necessarily higher, because here I have more of good X and more of good Y than I have down here. So in other words, this gives me higher utility than this point here, so this cannot be my optimal consumption. Okay, what about this level of utility? Can I reach that? Obviously not, since I am the entire indifference curve is in my infeasible set, right? There's no single point on this indifference curve that I can afford. So in other words, I want to be on an indifference curve that's as high as possible, but I have to make sure that at least one point of that curve is within my feasible set. But my optimal consumption bundle cannot be a point where my indifference curve crosses my budget line, because in that case, no matter how and where you cross, just figure that out for yourself, I can always do better by picking a different line, a different point on my budget line. Okay, so this one is exactly right? Because here there is still one point on my indifference curve that I can reach. If I consume here, then I can still afford that, but I cannot go on any other point on my indifference on my budget line and reach a higher utility level, because all these points necessarily give me lower utility than this indifference curve, since I consume less of both products. Okay. So you cannot do better than this one, right? This indifference curve is just tangent to my budget line. That means that if I move anything higher, if I would move to a higher indifference curve, then I would no longer have feasible points on that new indifference curve. Okay, so in this case, that means that A is my optimal consumption bundle. So, what should we do? We have a budget line. That's just given. We cannot change that. So that's the constraint that we have to deal with. Given that constraint, we have to try to reach an indifference curve that's as high as possible, but that still has feasible points, or at least one feasible point. One point that you can afford. So this budget line, this indifference curve obviously does not give me my highest possible utility, since I can do better. I can reach a point where my utility must be higher, since my utility here is higher than my utility there, and all my points here give me the same utility. So my utility here is not only higher than my utility here, but it's also higher than my utility there. So what we should do is pick an indifference curve that is as high as possible while still remaining within the feasible set. So there we go. We go higher, we go higher, we go higher, we go higher, whoops, and back, and that's my optimal bundle, right? We go as high as possible while still touching the budget line. Gee, that was fun. Let's do that again. So there we go. We go to an indifference curve that's as high as possible while still touching the budget line. So there we go, and higher and higher and higher and higher, and whoops, back a little bit, and that's my optimal point. So what that implies is that in this case, at least, if everything is nicely shaped and smooth, that the indifference curve has to be tangent to the budget line, right? Necessarily, they cannot cross at my optimal consumption bundle, as I have argued now. Necessarily, my indifference curve should be tangent to my budget line. Because if they cross, there's room for improvement. And if they have no points in common, then that level of utility is infeasible. Okay, let's do the math. Because the interesting thing is, so the slopes of these things have to be equal, right? That's simply what tangent means. But we know the slope of this budget line. We derived that a couple of slides ago. And we also know the slope of the indifference curve, because that was my MRS, my marginal rate of substitution. So in other words, slope of the indifference curve has to equal the slope of the budget constraint. The slope of the indifference curve was minus MRS, or in other words, marginal utility of x divided by the marginal utility of y, and that should equal the slope of the budget constraint, and that's just px over py, as we also saw before. Get rid of the minuses, and that gives me this condition. The absolute value of the slope of my indifference curve should equal the absolute value of the slope of my budget line. Mux over Muy should equal Px over Py. And if you do it the other way around, that's fine as well. So you can also put y on top here, just as long as you do it consistently. So you can also say Muy over Mux equals Py over Px. But let's stick with this one for now. That's important. And in fact, this is probably one of the most important things to remember in this course, so keep this in mind. And there will be many exercises in the tutorials and the practicals concerning this as well. Okay, so here's an interesting interpretation of that equality. Again, look at this equality, right? I can rewrite it a little bit. If I throw some things to the other side and throw other things to the other side, I can also write it like this. And that's interesting, because what do I have here? Here I have my marginal utility of product X. So what do I get extra in happiness if I consume just one more unit of X, or infinitesimally small unit of X? And what I have down here is the price of X. So if I buy one more unit of X, then this is what I get an extra utility. But if I divide that by the price, then what do I get? Essentially, I get the extra utility of my last euro spent on that item, right? If my marginal utility of X is 10 and it cost me 5 euros to buy one extra X, then I get a return, if you like, of 2 units of utility for each additional euro. What do I have on the right hand side? I simply have the same thing, but for product Y. So this expression here is simply the extra utility that I get from spending 1 more euro on product Y. Take how much extra utility you get from buying 1 more unit of Y, divide that by the price of Y, and you get the extra utility of 1 more euro spent on Y. So this magic condition that I derived from the previous slide, you can rewrite it, and then this simply says, well, the extra utility you could get from spending 1 more euro should be the same for all products. And if you have more than 2 products, then you can show that this condition also holds there. So the last dollar spent should give the same marginal utility across all products. And that makes sense, right? Because suppose that this one would be higher than that. So my last euro spent on X gives me more utility than my last euro spent on Y. Well, in that case, I would not be spending my money wisely, because I could buy a bit less of Y and lose some utility, spend that money on X instead, and gain more utility there, since this was bigger for X than it was for Y. So that doesn't make sense, right? If you get more bang for your buck for one product than for another, then you should just spend more money on this first product. And that's exactly what this condition says, so that's a good way to understand it. And it's also a good way to interpret this and to remember it, by the way. Okay, let me just skip this. We're not going to go into that. Good. An example. So here's an example of how we're going to play around with this kind of utility maximization problems in the tutorial, in the practical, in the exam, what have you. So suppose that I consume apples and bananas. This is my utility function, a Cobb-Douglas function, a to the power 1/2 times b to the power 1/2. And indeed, I already mentioned that, is known as a Cobb-Douglas function, and you will see it very often. Some more parameters for this problem. Suppose that the price of apples is 2, the price of bananas is 3, and your income is 60. Question: what is your optimal consumption bundle? What should I do, in other words? Okay, I can do that. So here again the parameters of the problem, and let me go through the analysis. So let me first draw my budget line. There we go. Price of apples is 2, price of bananas is 3, my income is 60, so that gives me this rather slow budget line. There we are. If I spend all my money on apples, I can buy 30, 60 divided by 2. If I spend all on bananas, I can buy 20. Good. Next step. Let me throw in some indifference curves. There they are. Which should I have? Well, obviously, this is my optimal consumption bundle, right? The one over here, where the two just touch each other, where the two are just tangent. Okay, so at the optimal bundle, the slopes of the indifference curve and the budget line have to be equal. That condition has to hold, the one you just saw. What is MUA? Just take the derivative of your utility function with respect to A. That gives you this. What is your MUB? Same story, but the derivative of your utility with respect to B gives you this. So my MUA over MUB, in other words, my MRS, my marginal rate of substitution, looks like this. The good news is we can simplify this thing a lot. And here, this is where your rules, your high school mathematical rules of manipulating powers come along. A to the power minus 0.5 is just 1 over a to the power 0.5, right? So I've thrown the a below here, and b to the power minus 0.5 here below in the denominator, that's just b to the power 0.5 in the numerator. So I've done that here. Oh, sorry. Not yet. First, I got rid of the 0.5s. They just cancel out. And the next step, I'm going to do what I just said, actually. Is just so make sure that I get rid of all the negative powers, essentially. What do I have left here? I have b to the power 0.5 times b to the power 0.5 left. Okay, I know that multiplying these two things gives me exactly b to the power 1, right? And downstairs I have a, so my MRS in this case equals exactly b over a. What about my price ratio? This thing over here, that's 2/3. So that's that. What do I know? So I know the slope of the indifference curve here. I know the slope of my budget line here. And I know that these two things have to be equal. So b over a has to equal 2/3. Okay, but I'm not done yet, right? So I know that at the optimal consumption bundle, this condition has to hold, and I can rewrite that a little bit. I can write it like that. So at my optimal consumption, I know that the amount of bananas that I consume should equal 2/3 times the amount of apples that I consume. But there's another thing I know, right? I also know that at my optimal solution, I satisfy my budget constraint. I spend all the money that I have. Okay, let's use that second piece of information. This is my budget equation in this case, right? This is the amount of money that I spend on apples, because the price of apples is 2. This is the amount of money that I spend on bananas, since the price of bananas is 3. And my income is 60. Hey, but wait a minute. I also know that at the optimal consumption level, B has to equal 2/3 of A. So I can plug that in there. I've done that here. And if I evaluate that, I end up with 4a having to equal 60. In other words, a has to equal 15. 2/3 of that gives me b, gives me the amount of bananas, so that should equal 10. So that solves my problem, right? If you could not follow all the mathematical steps along the way, here are the ones that I used. If you take a to the power x, take the derivative with respect to a. By the way, this is a way of writing a derivative, right? I should have noted that before, but in mathematics, economics, there are many ways to write a derivative. Just to confuse you, this is one of those ways. A to the power x, the derivative of that with respect to a, that's just x times a to the power x minus 1. The power goes in front, and the power decreases by 1. This is another thing that I used. A to the power minus x is simply 1 over a to the power x. And the third one that I use, a to the power x times a to the power y, is simply a to the power x plus y. You have seen this in high school, hopefully. Otherwise, you will see it in your mathematics course. But these things are good to keep in mind to be able to manipulate these Cobb-Douglas functions. Okay, that was fun. Let's do another one. Okay, if you insist, here's another one. Suppose I consume artichokes and beans, which conveniently also start with A and B. But now suppose that my utility function looks like this. So again, Cobb-Douglas, but a to the power 0.2, b to the power 0.8. Price of artichokes is 4, price of beans is 10, income is 100. What should I do? In other words, what's my optimal consumption bundle? Okay, same steps as before, so let me do it a bit quicker. At the optimal bundle, the slopes of the indifference curve and the budget line have to be equal. That was this condition. What is my MUA? Again, use the rules that I just showed you. That's that. This is my MUB. So if I divide the two, I get this expression here. 0.2 over 0.8, that's just 1 over 4, right? So that's what I've done there. Get a to the power minus 0.8 downstairs, b to the power minus 0.2 upstairs. Then I get this. And that leaves me with exactly b over 4a. And what about the price ratio? The price ratio is 4 over 10. So I know that at my optimal solution, b over 4a has to equal 4 over 10. And if I rewrite that a little bit, and again, these are videos, so you can just stop them, rewind them if it goes too quick, but just calculate along. But if I do that, I end up with b is 16 over 10a. So this is what my condition that the slopes have to be equal imply, right? There's another thing I know. My optimal consumption level is such that I spend all my money. This was my budget constraint. Price of artichokes, price of beans. My income is 100. Plug this thingy into that. That gives me this. So then 20a equals 100. So a is 5 and b is 8. By the way, in this example and also in the previous ones, these are nice round numbers, but they don't have to be, right? I also mentioned that before already. Which brings us to the quiz for 4.4. So you can feel it coming perhaps. This is a similar question, again, about artichokes and beans. This is my utility function. In this case, price of artichokes is 15, that of beans is 10, and my income is 200. What is my optimal consumption bundle? Please stop this video, calculate this, and then continue to check whether your answer is correct.